Okay, I've decided to make a little video here, continuing on from our lecture on Tuesday. Several students came to me after class and wanted me to continue this on to the full conclusion where we can actually uh, do a flow solution on this mesh that we've generated. Now, as you can see here, this is the coarse mesh, and it's the full volume mesh. We're not resolving this leading edge very well. But for this demonstration, this will be good enough. We just basically want to walk through the process of how we get a flow continuum in place, get our boundary conditions set up properly, generate reports that we would like to look at as we are running this thing, a scalar scene that we would want to look at, and just walk through the whole process of doing that from scratch. So right now we only have two scenes, the geometry scene and the mesh scene, and that's what we created in class. So we're going to create a scalar scene and follow on doing reports and everything else. So we're done with the mesh operations. I'm going to close out the geometry folder, and we're going to open the continuum folder. And you'll see now that once we generated the mesh, it automatically created a physics continuum. However, there's really nothing in there. It has no models to speak of other than the three-dimensional model, which is obvious anyway. So what we want to do is we'll right-click on physics and we'll select models. And generally, we want to always look up here in the upper left-hand box, and we'll pick a time, and then that'll go down to material, and it'll automatically repopulate that upper corner with what we want to pick on next. So right now, our enabled model is three-dimensional, but we also want to run steady state. We're not unsteady. We are a gas. We're not a liquid or a solid or a multiple component species. So we're a gas. Now, this one is not obvious, but what we want for this type of flow, we want a coupled flow, and that's going to be a coupled energy as well. We are ideal gas, and now if we were running a higher speed, greater than Mach 6 at a high altitude, we might want to do thermal non-equilibrium. We might want to do, if we're going in faster, real gas. So, but in our case, we're sufficient. We're running Mach 1.7. That's the ideal gas regime. We do want to run a turbulent solution. And now there's four turbulence models we can choose from: K epsilon, K omega, Reynolds stress, and Splart Alamaris. I generally use the K omega or the Splart Alamaris, and in this case, let's just use K omega. Now, the rest of the boxes are really optional boxes. We're not going to do a transition model. So right now, all the enabled models that we have are sufficient, and we can close that out. So what is populated in the physics continuum are our models. So here's all the models that we've chosen, and there are some defaults that just pop up when you pick one. But one of these we have to change, and it's only one, and it's only because we have the possibility of running some really low pressures because we're running supersonic flow at a high altitude. So under coupled flow, it has under the properties box, you'll see it has a minimum absolute pressure of 1,000 pascals. I don't think we're going to run into a situation where we're under that, but just to be safe, I like to make that 100 pascals. So that way it won't clip it at 1,000. It'll clip it at 100, which is better if we are running at higher altitudes and higher speeds. So really, that's the only thing you have to change or even modify at all under models. Under the reference values, we don't really need to worry about these minimums and maximums. They should be fine for our case if we're running, again, higher speed and higher altitude. We might have to worry about this maximum allowable temperature and the minimum allowable temperature, but the defaults are fine right now for our case. Now, the reference pressure comes up as a default of the atmospheric pressure. uh, at zero altitude. Generally, we could set this to be our pressure at altitude, and in our case, we're running at 41,000 feet, so our pressure would be 2.59 psi. But I don't really want to do that, because then all our pressures, when we're doing plots, and if we did, line plots of pressure, there would be gauge pressure. I'd rather have the absolute pressure so I know exactly what the pressure is. So I generally tend to make this reference pressure 0. Okay, so now everything is going to be absolute pressure. So that's really all we need to change under that. Under initial conditions, now when we specify the flow field variables on our region boundaries, our free stream boundary and our outflow boundary, those can be specified by picking our Mach number and our altitude. We can't do that in these initial conditions. So what the difference between these are, the free stream will always set the values that we put there. They will always be constant and coming in, from the outer boundary. For the initial conditions, it gives us a starting point that is not as abrupt as starting with everything set to 0. A lot of times, if you just don't specify anything for initial conditions, it'll blow up, meaning it'll stop running on you, because it's such a severe change from having 0 velocity, say for instance, to a flow field coming in from the boundary at Mach 1.7. That's just too big of a change, and the flow solver can't do it. So we like to put an initial condition in here that's fairly representative of the free stream values. But again, we can't specify it by Mach number and altitude, so we need to actually go and find out what the altitude pressure is and temperatures are at 41,000 feet. And we know that at our 41,000 feet, we're at a pressure of 2.59 psi. Okay, and again, the default units are usually metric, so it's pascals. But if you type in psi, it knows the conversion and automatically does it, so you don't have to worry about it. Our static temperature is 389.97 Rankine, and again, that's at 41,000 feet. At our velocity, we know we're at Mach number 1.7. So we can calculate, and with that altitude, we can calculate the velocity, and that is equal to 1645.46 feet per second, and it's in the x direction. If your first solution is running at an angle of attack, you can put in, the direction cosine values of the velocity there. But now, be careful, because it's set to meters per second. We want to change that to feet per second. And again, it knows the conversion. You don't have to worry about that. So we're good on our initial conditions. So pretty much our physics continuum is defined, but now our boundary conditions are still undefined. So we need to change those on our free stream. And right now it has flow direction, Mach number, pressure. Well, we want to specify these by altitude and Mach number. So we need to go back to physics conditions, and the free stream option tab, we want to click on that and go to the properties box, and we want Mach number and altitude. Instead of Mach number, pressure, and temperature, we want to just use the altitude. So we can turn that on. That's all we need to do in there. And let's make our altitude 41,000 feet. We're good there. Now our flow direction right now is just set to 100, so it's going to come in along the x-axis. As you remember from before, we used a table to do that. Well, right now when you're coming in from scratch, that table doesn't exist. So let's go get that table. And if you have your previous solutions that had the template in it, that table exists, and you can just export that table and then read it back into this solution. So let's go right click on that, and we want to do a new table, and we use a file table, and I have that out here, and it's AOA positive, because again, we only need to run the positive angles of attack and then mirror them in our spreadsheet later, because this is a symmetric airfoil. So I'm going to pick that. So now that table exists. Let's just tabulate that and just make sure it's the right thing. And it's the first 1,000, it's at 0 angles of attack, and then every 500 after that it changes. So this is the same method that we used before, and everything looks right. We've got our X component, Y and Z component, and they look right. So we can close out on that. So now we have our table read in. Go back up to our free stream values, pick our flow direction, and right now it's set to constant. We want to change that in the properties box to a table, an iteration table. And remember, our table had iteration values in it. And then click on that table iteration box. We want to pick a table, but right now none is specified. And there's only one table in there that shows up, AOA positive. Bring that in. Now, this is very, very important. Our interpolation right now is spline. So what will happen is, between the different angles of attack, they're not going to change like a step. They're going to change continuously, and this solution will be meaningless. You won't know where you're at. So you need to make sure that this is set to step. Okay, so now your X data is set to null. You need to fix that, and that goes to our X value. The Y table data is our Y value. Our Z value data table is Z. And so we're all set to go with our flow direction. Our Mach number we know is 1.7. And our pressures are already set because we picked altitude and Mach number. So those are already set. So we're done with specifying our free stream conditions. The only other boundary that we have to specify is our outflow condition. Now again, under outflow, it doesn't have the capability of picking altitude and Mach number, so we actually have to go in and put our pressure in there. This 2.59 PSI. And our static temperature is 389.97 Rankine. So that's all set. That's ready to go. So really, right now, we're ready to run. But we don't have anything to view any of our solution as it's running. And we do need to make some modifications to the flow solver itself. So right now, the flow solver that we're using is the coupled implicit flow solver. If you click on that, you'll see that the Courant number is set to 5, and I wouldn't mess with that for our solutions, but you can adjust that to get your solution to converge quicker, or if your solution is diverging, you want to lower that number, but we won't worry about that right now. We'll leave that at the default value. But one thing that we do want to do is we do want to do an expert initialization, which is grid sequencing. So we click on that. Right now it's set to none. We want grid sequencing, and what that does is it divides up this final mesh by several layers. So you're ended up with your first layer is a very, very, very coarse mesh. You solve the solution on that really quickly. You interpolate that to a denser mesh, so on and so forth, and it does it like 8 times until you interpolate that solution to the finer mesh, and then you initiate your solution in a normal fashion. So this really helps speed up the convergence of our solutions. So that's one thing that we want to do there. The other thing is our stopping criteria. Our stopping criteria right now is set to 1,000. Well, we know we want to run to 6,000. for all of our what's in our table. Let's just make sure that that's right, and we'll tabulate that again. Right. So the last time it changes the angle of attack is 5501. So at 6,000 we should be done. Okay, so that's all, setting up everything to run, but we still have nothing to look at. So right now we want to create some reports. So let's right-click on that, and we'll do a new report. And the top box will show us a whole bunch of options, but we want a force. And let's rename that to axial force. All right, and now in the properties box, the units on that are newtons. I actually like to use English units, pound force, and that's totally up to you. It doesn't really matter. It's just my own personal preference. The direction is correct, 100. So this is in the axial direction, and the only other thing that we need to worry about is what parts are defined. But I'm going to wait on that because I can do all the reports at once because they're all going to be the same parts. So rather than do this 3 times, I'll do it once at the end. So let's create another report, another force report, and now we'll rename that to normal force. And again, go to our properties box, change it to pound force. Now our direction is not right. We want 001. We wanted it to be in the Z direction. And so we'll change that. And again, we'll pick our parts later. So the other thing that we want to look at, we're running a symmetric solution, so we don't have yaw and we don't have roll. We really only want to look at one moment, and that is our pitching moment. So I'm going to rename that. And again, the units, I like foot-pounds. And the axis is wrong. We want 010. The axis that we have the rotation for pitch is the y-axis. So we want to get rid of that and change that to 0. Reference pressure, don't worry about that because we've set our reference pressure to 0, so that's good. The axis origin. Now, if you generated this horizontal tail or canard or whatever control surface that you are going to use at the quarter chord point to be your 000 location, this is fine. If it's not at that location, you probably want to change it to that location, or you're going to have to change the moments later on. Now, one trick is, let's say you run the whole solution and you have the wrong origin. Well, it'll only work for the last angle of attack. You can change it and redo the report, and it'll change it. But make sure you get it right, because if you don't, the only one that'll be valid is the last one. So right now these reports are all set up, but they don't have any parts associated with them. So I'm going to select all of them, and I didn't want to do that. Stop that. Okay. So we want to go to parts, and we're on regions now. We're not actually a part. We're doing the flow solution, so we need to worry about our regions. I'll select them all, but I do not want free stream, I do not want on flow, and I do not want symmetry, because those are not walls. Those are not going to give me an accurate representation of my forces and moments if those are selected. So you got to make real sure that those don't get selected. So we have these 3 reports, but what we want to make a plot out of them. So I'm going to do create monitor and plot from report. You need to create the monitor, or you can't do a plot with this. So you'll notice that you can't just go straight to create plot. You need to create the monitor and plot. And it's going to ask you, do you want 3 plots, an axial force, a normal force, a pitching moment, or do you want to put them all on a single plot? I'm going to just put them all on the same plot for now, because you can change the axes. You can have the moments be on this axis and the force be on this axis, or any way you want to slice it. We'll maybe do that later on. But for now, we've got our plot ready to go. But we still don't have any contours that we can look at, so we want to do a scalar scene. So we'll do a new scene, scalar. And right now it defaults that the outline of it defaults to the region like it should, but the scalar value, and you'll see I clicked on the scene plot, the outline already has the proper parts selected, and it has all the boundaries. I'm going to get rid of that outer boundary just because it doesn't really serve any useful purpose. So now we'll just have the horizontal tail. And then if we go to scalar, we need to pick what parts we want. And I want to pick all the wall surfaces for sure. I like to look at the symmetry and the outflow. We may as well put those on there. Free stream will just cover up everything, so we don't want to put that on there. And so there is where our contours will be. Right now, there's no function selected. So we go to click on that box, and then you'll bring up your property box, select function. And there's really there's four field functions that I like to plot, and you really don't need to look at any other ones. These absolute pressure, these can be misleading. So what you like to look at is basically Mach number. So we can plot, and you click on that box and then click the lab reference frame. So right now that will plot Mach number. Another field function that I like to look at is static pressure. And use this. When you're looking at pressure, use this one. Don't use any of the other ones. This one will give you the true static pressure as defined by your reference pressure. So if you're running 0, this will give you the absolute value of your static pressure. Again, you can do total pressure, same deal. I don't usually use that much. Another one that I like to use is temperature. That is your static temperature. So, it doesn't call it out as static temperature, but that is the one you want to use. And then the other one is velocity. Okay, so under velocity, velocity is a vector, so you can plot any one of the components of the vector, but generally you want to plot the magnitude of that. So let's change this back to Mach number for now. And so now we have everything ready to go. We have a scene. We have plots that we can look at as it's converging. And we can run it. So let's click the little running human here. And that will, if you click this will do the grid sequencing and then stop. If you click this, it'll do the grid sequencing and then immediately go into the flow solution. Let's go ahead and click that and let her go. And see, it's creating 7 layers. Sometimes it does 8, sometimes it does 7, sometimes it does 6. And you'll see each time it's getting a little more dense, and it converges to a certain level. I think when the continuity gets less than 0.1 or 0.05, there we go, 0.05. So as the level of grid sequencing goes down, or level 3, now we're at level 2, you'll notice that it's actually starts to slow down a little bit because you're getting on a denser and denser grid. So the residuals haven't even kicked off yet because we're still just basically initializing the grid with what we would like to start with. And we're on our level 1. So when this level reaches 0.05, it should kick off into our regular solution. Now, if we look at our scalar scene, it's really not done anything yet. It's kind of defaulted to 1.7, 1.694. But we're getting close. As soon as it converges our level 1, it will put the solution on there. We'll be able to see it, and then it will commence the solution, the regular full grid solution. So we're finished, and there it is. But it doesn't look very interesting yet. And it's limiting some things right now. Corrections are limited. And that happens in the early part of the solution. If that's happening all the way through your solution at the very end, you might want to look at what a potential problem could be. One of the other things you'll notice, these contours are kind of lumpy. I generally like to go to under scene plot, under scalar. Right now, the contour style is automatic. I like to use smooth filled. And these are all my own personal preferences. None of these things, you know, there's a lot of options here. You can use all different kinds of color bars, for instance. Look at the different kinds of color bars you can use. And, you know, do whatever you want. It doesn't, that kind of stuff doesn't really matter. You know, it's your own personal preference. So now you see it's already, you know, you're already starting to see some shocks forming. If we look at our residuals, they're starting to converge. We look at our reports, they're starting to settle down to a value. But, you know, we're going to let this run 1,000 iterations, and then the next angle of attack will be for 500 iterations. You kind of want to let that first one, you know, really settle out. But as you can see, you know, it's already looking good. We're running. And if you have any questions, feel free to email me at any time, and we can do a Zoom meeting like this. And we can show you other things that we can do with StarCCM. So I hope this helped. I hope the people that want to know more about this, you know, use this opportunity to look at this, and we'll talk to you in class next week.